qui va nous donner ce grand séminaire. Donc Clara était une scientifique du NK, National Center for Atmospheric Research, à Boulder dans le Colorado. Clara, elle a passé sa carrière, une grande partie de sa carrière à étudier la variabilité climatique à différentes échelles, aussi bien océanique qu'atmosphérique, continentale. Donc, elle a publié de très très nombreux papiers, elle travaille sur la glace de mer aussi. Et puis récemment, elle a été un peu pionnière dans le développement de ce qu'on appelle les grands ensembles à conditions initiales. Et c'est un petit peu de ça dont elle va nous parler, des implications pas philosophiques, mais presque de ce que ça veut dire. Voilà. Donc elle a développé ça depuis plus d'une dizaine d'années. Elle est membre de l'Académie des sciences américaines, elle est AGU et MS Fellow. Et puis voilà, c'est un grand plaisir de l'avoir ici. Clara, le floor is yours.
Oui, merci Laurent. Merci à tous de venir pour écouter ma lecture et I will continue in English. Mais je comprends français aussi. Alors, I want to speak about, as Laurent said, how we understand our regional climate in the past and in the future. And we have to account for both natural variability and, of course, external factors, including how humans are changing our climate. So I'm going to keep it very high level so that it's more conceptual, and feel free to ask me questions anytime. So it's just in a nutshell, this is the message. We can have, take one of our IPCC climate models that we use for making projections for the climate in the coming decades. And then we can apply one particular radiative forcing pathway. This could be a projection of CO2 increase in the future and other aspects of human-induced climate change. But 1 + 1 does not equal 2. In fact, it equals a wide plethora or range of outcomes that we can have just with one model and the same radiative forcing, the CO2 increase. But we can get, because of this natural climate variability, we can get a range of outcomes. And these, I use the roll of the dice to show that this is an unpredictable range. We have very limited predictability beyond a few years to maybe a decade in our climate system. And so beyond that time scale, this internal climate variability really just is a roll of the dice. It is random, unpredictable variability. So that's the story. And now I will just show you evidence of this from one climate model and applied to European wet climate. So I'm just going to show you one model. Here we use the NCAR, the latest NCAR global coupled model. I will explain that a little bit more detail. So this is my example, and we use a pathway of CO2 increase that gives a global increase of 3 degrees Kelvin globally by 2070. So it's a very strong increase in the CO2. And then we run this model 100 times. So we run this from 1850 all the way to 2100, 100 times, and only change the initial condition ever so slightly. So let me show you then from these simulations what the wintertime precipitation and the atmospheric barometric pressure, I'll call sea level pressure, SLP, the change over the next 50 years, from today to 2071, so roughly 50-year time scale. And I think the colors don't show up very well here, but hopefully you can, if you're interested, you can see the talk online and you can get better color. So here is one realization of all 100 possibilities. And this one shows a future change that will produce a low pressure system centered over the UK. And that brings storms into Western Europe and increases the precipitation. So this is one outcome. I chose it, it's the fifth of wettest of the 100 simulations. But this is one outcome that our model predicts for the next 50 years, the trend in the next 50 years. And now let me show you another outcome. This was the fifth driest of the 100 simulations. And this one produces a high pressure sitting over Italy and that area. And along with that high pressure, it's hard to see the color, but there is drying, reduced precipitation in that area. So these two outcomes couldn't be more opposite, but they are each plausible, and they can each are produced when the model is, when you increase the CO2 by this radiative forcing pathway. So that is a wide range, and here in the middle is when I average all of the 100 realizations from this model. And when you average them, the roll of the dice, the internal variability, which is random phase, random sign, and amplitude amongst the members, that all averages out, and you end up with the anthropogenic component. So this is when we have enough ensemble members or realizations, we average out the internal variability, the natural variability. And this then is the model's prediction of the human component of climate change. And you can see that the sea level pressure contours, there are very few of them. So this model, like many other models, has very little dynamic atmospheric circulation change. And you can see drying over the southern portion of the European region and increased or wetter conditions to the north. So again, my take-home message is that we know we can estimate the anthropogenic component from this large ensemble, but what's equally important is that we have to be ready for a range of outcomes, because we don't necessarily get the average. We will get one single realization. And here is just a histogram or showing the range of precipitation trends across all 100 members when I average over all of this European region. And you can see the 5th to 95th percentile is, goes very wide. So again, this is just showing that we have inherent uncertainty in our future trends or projections. And now let me show you the same thing for air temperature. It will be easier to see with a color scale. So again, this is one realization. I chose it. It's the 5th warmest for this region of the 100. So it's like the 5th percentile, if you will. And that shows warming everywhere and strongest warming as we go further east. And then here is another realization from the same model and the same CO2 increase, and you see much weaker temperature rise, even though it has the same increase in greenhouse gas. And you can see that the circulation, the high and low pressure are very different amongst the two members, which explains much of the difference in the temperature trend. And then we can average, so that's the range of outcomes. And I think of it as the 5th to the 95th percentile, so very plausible. And then we can average all 100, and that is this model's result for the anthropogenic component. So warming everywhere, as we expect from physical principles, but it can look very different in any single realization. So one can make maps like this for any region, any season, any length of time, and qualitatively one finds the same results. And then this is just the range of temperature change across all 100 members, and it can range by a factor of 3, which is enormous in terms of adaptation and planning. Okay, so the rest of the talk will be then to, discuss some of these results. So first of all, I just want to highlight some of the implications of this range of outcomes. So the first is, and as I've demonstrated here, internal climate variability, this roll of the dice on long time scales over a long time periods, really limits the accuracy of information that we can give to policy and managing resource managers. It doesn't. We're giving them the correct information, and we just have to say that it is uncertain within, or it can take a range of outcomes. And then you have to ask yourself, well, how do you evaluate a climate model given this wide range? Which do we believe this climate model? So it complicates that, and I'll show you a little bit about that. And then finally, as I'll show you near the end of the talk, it actually makes the interpretation of the changes that we've already observed, it makes it quite challenging to parse the anthropogenic component and the internal variability. And then then it raises a number of open questions and challenges. And as I've already said, how do we even address how realistic are our climate models? The forced response, that's this average, if you will. How realistic is that? How do we even address that question? And then how realistic is this range of outcomes? How realistic is the model's natural variability? And then, as I alluded to before, the real world, we only have one roll of the dice that we have lived in. And so then how do we evaluate models given that our observed climate history is only one of many possibilities, which is kind of strange to think about, but I think it's very important. And then last, could an alternate outcome in the real world have occurred? And if so, what might it have looked like? So I'll show you some of these things as we go along in the talk. So first, just very broadly for people who are not in the climate variability field, I wanted to talk a little bit about the sources of internal or natural climate variability. And I want to show you how these large ensembles of climate model simulations are conducted. How do we go about evaluating climate models? And then my favorite part I want to show you is building or constructing an ensemble just from the observed climate record. What could the outcomes have been? And then finally, some points, summary and outlook. Okay, so sources of, I use the word internal, but it can also be used as natural. So this is variability like El Nino and La Nina events, or you've heard of the Atlantic multi-decadal variability. These are natural processes within our climate system, and they arise spontaneously. They are not driven by changes in the sun or changes in volcanoes or anything. They are just internally generated. So very important aspect that we forget, I think, a lot is we're so familiar with the day-to-day and week-to-week changes in our weather, and we all are very familiar with how changes in the position of the jet stream can produce very large scale, here for the US, changes in temperature and precipitation. And we think of this as occurring on very fast timescales. But actually, the predictability, well known from pioneering work of Ed Lorenz and many others, there's really a predictability limit of several weeks in general, at least for the jet stream. So very limited predictability, and this can be modeled as sort of a nonlinear stochastic process. But for us here, for this topic, what's really important is that even though these are very high frequency fluctuations, they do not average to zero over long time scales. There is some residual variability on long time scales, and it's completely unpredictable, and it's just the way the fluid works. And that is behind a lot of the wide range of outcomes that I showed you at the beginning. Then we have another whole class of phenomena that arises because the ocean and the atmosphere are tightly coupled. And El Nino Southern Oscillation is a very prime example, and we have these other phenomena that have been discussed in the literature on longer time scales. But again, for us, the important thing is their predictability time scale. And again, it's limited, and maybe this will change with advances in our field, but at this point, really very much limited to less than a decade. So anything that we project or predict beyond that, there is really zero predictability. And then the ocean can also have its own variability. I won't discuss that very much at all. Okay, so now I just want to keep it on this level of kind of conceptual. So the sources of internal climate variability, I've kind of highlighted them here next to the dice, because, and their predictability time horizon, weeks to a decade. And so it's really, I don't know how you say this in French, if it's a useful icon here, but it's a roll of the dice beyond the time scale at which you can predict these phenomena. So, and then this is what really is underlying these challenges for our ability to predict and project climate into the future, how to evaluate climate models, and how to attribute the observed changes that we see. So now I'm kind of, backing up, and I'm going to show you how these climate model large ensembles are designed. They're relatively new in our field, maybe by now, I don't know, 20 years, something like that, but it's really taken off in the last 5 years. I think global climate modeling centers now recognize, fundamental importance of running these large ensembles. So, as I say, it's sort of the go-to, it is the way now forward for studying climate variability and change. It's not to say that machine learning could also be very valuable, but I think we have to begin with our climate models. So what I want to show you, the maps I showed you at the beginning, they come from, of course, I'm very familiar with this community Earth system model that is built with the university community at NCAR. And we have a couple of papers on these more recent large ensembles. So here is how they are designed. And so they are global models. They do not resolve anything, finer than about 100 kilometers. So we don't use them for, local and regional purposes, but they give you the large scale, and they contain representations of the atmosphere, ocean, cryosphere, terrestrial system, and a little bit of biology, both in the ocean and land. So when we first designed the CESN1 large ensemble, this is how we did it, and I think people were really surprised at the outcome. So first, this is the way the IPCC climate simulations are all conducted. You begin with a pre-industrial control run, and the model, comes into a sort of quasi-equilibrium and has its own variability. And you run that long enough that you have some kind of steady, not steady, but equilibrium state, I should say that. And then we ran the model, and it looked, like it was in radiative balance. And at that point, at the year 401, we then continued the simulation all the way out to 2100 with known historical changes in CO2, volcanoes, solar, etc. And then the RCP 8.5 pathway to 2100. This is all very standard in the IPCC protocol. And then what's new is that on the 1st of January, we introduced a round-off error in the atmospheric temperature. We perturbed it by 10 to the minus 14 degrees K, right? That is from one computer system to another. That's completely, it's infinitesimal. So tiny change in the atmospheric temperature on that date. And then we ran another 39 simulations. I used the butterfly to indicate how small the initial condition perturbation was, the butterfly effect. And then these, to the extent that these simulations then diverge over time, we know by this design that their spread over time can only be due to this internal climate variability that is irreducible, and it's largely unpredictable. And then, as I showed you before, you can isolate the radiatively forced component when you, at each location in time, if you average across all of the simulations that you have. And that's what I showed you earlier. And yeah, the CSN2, for those interested, we have 100 ensemble members, and they all start in 1850. So it's an enormous resource for the community to study climate variability and change. And then the last thing I'll show you is this is the global mean surface temperature. So the planet as a whole, the global mean temperature, and this is the control run and the first member. And then you see in the gray shading what each member looks like. And you can see that the observations lie very nicely within the model spread. And you can also see, as expected, that there's little spread in the global average. It has to be that way because the planet is in some kind of, radiative balance. But there's, of course, very large spread amongst the members regionally, as I showed you at the beginning. Okay, so now I'm going to come to a few points, and then we can just have some time for questions. So climate model evaluation. So how do we go about this? It's more complicated now. So how should we evaluate modeled trends or trends from the climate model given a single observed outcome? How do we assess our models? So, of course, a very straightforward thing is you can determine, so let's say we make a map of temperature trends from the observed data and then from the model, and you can determine whether the observed trends lie within the spread of the trends from the model. And so here are the results for Europe for the last 50 years. Precipitation on the left and temperature on the right. And you can just pay attention to the blue, the boxes there. That's for the 1972 to 2021 period, the change over time. So the observed value is given by the black dot. And you can see that for the CSM2 and the CSM1, which I'm not showing you, that the model range is, it encompasses the observed value. So there's no discrepancy, and we can say we have, at least by this measure, the model is credible. But of course, that's a little bit too simple, and it's helpful, but it's really insufficient because perhaps the model overestimates the magnitude of natural variability. Then its spread can be very large and it can be false. It's too easy for the observations to lie within it. So that's a false positive. And then also it's very hard to tell the forced response in the model, which is the average of all the members given by the white line. We have to assess if there is a bias, which there likely is, in the forced response. So this is a helpful metric, but it really is insufficient for properly evaluating our climate models. So I think it's of course, there are many approaches now, and I'm just going to show you what I think is useful, not the only approach by any means, but to construct plausible alternative outcomes based on the observed data. And i.e., I call it the observational large ensemble. And I'll walk you through what that is, but it's very analogous to what the climate model large ensemble. So it's challenging, it is kind of cutting edge work, and I think could benefit from new approaches that are being developed in the machine learning realm. But I'll show you what we've done and how it is very illuminating. So a few years ago, or maybe quite a few years ago by now, I had a postdoc, Karen McKinnon, from kind of the statistics and climate world, and she put together a very nice kind of straightforward way to construct all synthetic sequences of this natural variability based on the observational data. So you can think about El Nino and La Nina events occur randomly over time. The trends that you estimate. So we can construct these synthetic sequences, and then we can add them back onto an estimate of the force response. I'm well aware this is getting a little bit in the weeds and technical for many of you, but you can just bear with me and you'll see the maps in a moment, what they look like. And then we can test how well our method works by using the model large ensemble. We can apply the method to each member and see if it reproduces the spread that we find across the entire ensemble. And that's a very valuable use of these model large ensembles. So I'm just going to go through this for some people online also, but don't worry about the details. But first you have to remove an estimate of the forced response from the observed data, and this is still ongoing work, how to do that. And here we've used a couple of approaches. There are many more that could be used. And then step 2, you can take these leading modes of variability that we were looking at before, and you can remove them empirically by regression. And then you have residual variability that we term the noise, climate noise. This is a term used in climate science, and it is mainly due to internal atmospheric dynamics. I haven't shown you that, but there are many references for that statement. And then we compute these surrogate sequences of these modes of variability and surrogate sequences of the climate noise. It's all from the data. And then you add them back onto the forced response. And then you have like all these realizations that are consistent with the statistics of the observed climate record. So I'll just come back now. I know it's very faint. You can't see the colors with this projection, but I'm going to come back to, it's a slightly longer time period now. These are over the last 60 years, from 1962 to 2021. This is what the observed precipitation trend or change and the observed sea level pressure changes were over this time period. So we had a trend towards lower pressure to the north and higher pressure to the south, and not surprisingly, there was increased precipitation over much of northern and central Europe, and then decreased precipitation over the Mediterranean area. So that's what we observed. But this doesn't have to be the only thing that could have happened. Just if you think back to the climate model large ensembles, we know there could have been many outcomes. So what does our procedure with the observational large ensemble, what does that show us for the range of alternate realities, if you will? So I will show you that here. So first, if you look at the middle map, you see very little color and you see no contours. So that's one estimate of the forced response, and I'm not going to go into detail how we obtained that. I know it's not that important, but there are different methods and you get roughly the same very small amplitude. And then I can take from our observational large ensemble, we have 1,000 synthetic realizations that we produced. And here I'm showing you the 97.5th percentile for precipitation over Europe, and then the 2.5th. So I'm showing you the full spread or plausible spread that we have constructed. And you can see that you get very different, we could have lived through very different trends over the last 60 years. It could have been very wet, getting wetter over the Mediterranean and drier over Northern Europe, or we could have had the opposite. And in fact, this is what we got. But this doesn't have to lie in the middle. It can lie anywhere in its distribution. But the point is that we could have had either of these, but we ended up with this. Okay, so this is not the only possibility. Just like with the climate models, we can have a range. So now I'll show you what the CSM2 large ensemble for this same time period gave us. And they don't have to be identical. I haven't chosen them to be identical, but you can see there's enormous correspondence between the range of outcomes in the model and the range of outcomes that we find just from the observational data alone. So I think this is a powerful a way we need to use to assess our climate models, forced response, and their internal variability. So now I come to the summary and the outlook, and I just have a few messages to give. So I haven't shown you this precisely, but please take my word for it, and there are many publications that we have, I myself and many others, that this idea of chaotic atmospheric dynamics is a major contributor to the internal variability, natural climate variability, And that's what creates this range of outcomes for both trends in the past, historical, and trends in the future, projections, at these regional scales and long time scales. And then this range is largely irreducible because of this limited predictability on decadal scales. So we know this is just an aspect of our climate system. We can give very good information about the range of outcomes for water managers, industry, etc., policymakers. But it's important to give them the range, and it's not just a single number associated with human-induced climate change. And then I think I've shown you that we now need to have a new perspective on how to evaluate climate models and also attribution of the observational record. Because, as I've shown you from the observational large ensemble, alternate realities are possible. And I think that's a very powerful message that comes from the climate modeling large ensemble work back to our observations. And then I think I've shown you that the so-called initial condition perturbation large ensembles with climate models are providing us with, continue to provide us with new insights and understanding. And then I haven't shown you this directly, this dynamical adjustment, but again, I think this is observational constraints on our climate model outcomes. And then I'll leave you just with a couple of points of outlook. A new direction in our field, as you probably have heard about, is if we can, with these global coupled climate models, if we can refine the spatial scales so that they incorporate more local processes, for example, eddies in the ocean, mesoscale complexes in the atmosphere, will we get a different picture from our climate models? And so in particular, will the forced atmospheric circulation response become stronger relative to internal variability? Will there be an improvement in decadal prediction skill, in which case it's not just a roll of the dice? And I think, there are hints, perhaps, that the answers will be yes, but I think it's very open questions at this point. But this is sort of where our field is at the moment. And then, I also bring in, these beautiful AI methods that really can be brought to bear both on climate modeling and also on understanding the observed climate record. We have a project called Enforcement that is trying to bring the community together to do that. So I think I will leave it there, and I'll just show you, I'd like to end with, if people are interested for their own work, we have a bunch of tools and resources that we've developed over many years in my group. And for those working with climate model large ensembles, I can point you to a very nice diagnostics package, an archive of data, and then information in the climate data guide on the observational data set. So hopefully these may be useful in your own work. So thank you very much, and happy to have questions. Yes?
Great.